Beneath the familiar firmness of soil and stone there lies no seamless hole, no continuous crust, but a puzzle cracked rigid and restless. The earth, for all its appearance of permanence, drifts in slow, imperceptible motion. This movement begins not at the surface, but in the quiet divide beneath our feet, where the solid outer shell of the planet known as the lithosphere rests upon a deeper layer called the asthenosphere, warmer, weaker, and capable of flow. These two layers together hold the secret to a planet that breathes in stone. The lithosphere itself is not one solid piece, but a collection of vast plates, some carrying continents, others ocean basins, all floating atop the ductile mantle below. They move slowly, sliding past one another, colliding, diverging, vanishing. Each plate is bordered by zones of activity, yet in the vast interiors the rock remains still for eons as if asleep. These plates are thick sometimes, over 100 kilometers deep, yet the forces beneath can make them glide with the ease of icebergs on water, over timescales so immense they render mountains transient. What appears eternal is in truth shifting. The surface of the earth is therefore not stable ground, but an ongoing rearrangement. This quiet truth hides beneath the shuffle of daily life, beneath cities and forests, deserts and seas. Beneath the smallest insect and the tallest peak, the ground itself is drifting. The illusion of stillness is only human, the planet does not cease. The names of the plates themselves speak in vastness. Pacific, Eurasian, African, Antarctic. Each one spans thousands of kilometers. Each one carries the weight of landscapes and weather, species and civilizations, and yet none is fixed. The very crust that gives us ground to walk on was never meant to last. Even the oldest granites, preserved from an earlier world, bear evidence of transport minerals formed at depth surfaces reshaped by collision. Beneath continents lie roots of craton ancient rock stabilizing the centers, but even these are not immune. Through geologic time they too are folded, buried, or pulled apart. The surface tells only part of the story. Deep beneath the asthenosphere moves with slow pulses, soft and steady. It does not boil, it does not surge, it flows. Heat from the Earth's core rises while cooler rock above sinks. This convection, unseen and patient, is the mechanism that drives the lithospheric plates. It is not violent, not sudden. Rather, it is a planetary exhale stretched over millions of years. Some scientists compare the plates to lily pads drifting atop a slow, viscous pond. Others describe it as the skin of a heated stew, cracked and shifting. Yet neither image quite captures the scale, the unimaginable force of a process so silent it goes unmarked in human memory. In some regions, these plates move apart, creating space for new crust to form. In others, they collide, crumpling into mountain ranges or diving beneath one another into the mantle's depths. But everywhere the story begins with this quiet boundary between the brittle lithosphere and the yielding asthenosphere, the place where motion begins. It is a strange irony that the most solid-seeming part of the earth is in constant movement, while the soft mantle beneath offers the resistance of stone. Another irony, this process which shapes continents and oceans operates so slowly that even the rise of civilization has barely captured a flicker of its dance. Only took a few billion years to notice. Even today the science of plate tectonics is young. It was not until the 20th century that the idea gained consensus. For centuries the idea of a moving Earth was unthinkable. The continents, after all, seemed permanent. But the fit of coastlines, the matching rock strata, the fossils of similar creatures found an ocean apart. These quiet clues began to add up. The planet left its fingerprints scattered in stone. The poetic detail hides in the fact that even the deepest layers of rock buried miles below the surface can record their journey. Minerals align to the Earth's magnetic field as they form. When the rock solidifies, they hold that alignment like a frozen compass. These paleomagnetic markers tell us where the rock once lay, revealing how continents have drifted, rotated, and realigned across eons. Yet despite these insights, mysteries remain. We still do not know precisely how plate boundaries initiate. We do not fully understand why some plates survive longer than others, why some subduct quietly, while others trigger great earthquakes. The deeper mantle remains hidden from direct observation, known only by the whisper of seismic waves and the mute signals of gravity. These unanswered questions sit quietly at the edge of knowledge like stones at the boundary of a deepening tide. And perhaps the final irony is this: the very science that reveals the planet's restlessness gives us a kind of stillness. It reframes the briefness of human time not with dread but with awe. When we grasp that the ground itself is transient, that continents drift like ice on fire, then we begin to see how temporary even the tallest structures are. A temple, a mountain, a supercontinent all pass through the same gate of time. The plates move in their own rhythm. They are not fast nor slow, they are simply patient. The shell of the earth, broken and rigid, forms a mosaic that slowly shifts across the mantle's flowing heat. These fragments, tectonic plates, do not sit still. They do not lock into place like puzzle pieces. Instead, they jostle, drift, and rearrange, caught in a planetary choreography that unfolds over hundreds of millions of years. Some plates grow, others shrink, some split apart, others crash together. They grind silently, shaping the face of the earth without pause, without intent, without memory. At first glance, the surface seems stable, but stability is illusion. The continents are passengers on these drifting slabs, carried along like rafts on a restless ocean of stone. The ocean basins themselves ride along these plates, changing depth and contour with time. A continent that once basked at the equator may now sit near the poles. A coastline that once faced the heart of a supercontinent now meets open sea. Even now the plates are in motion a few centimetres a year, about as fast as fingernails grow, and yet across geologic time such gentle drift remakes the world. The slow rupture of a plate boundary begins with heat and tension. Deep beneath the crust, forces build and the lithosphere stretches, thins, and eventually cracks. A rift valley forms like a wound in the continent. Over millions of years this scar widens. Magma wells up from below, hardening into new crust. What was once one land becomes two. Oceans are born this way quietly. In eastern Africa, the Great Rift Valley marks the slow birth of a new sea. Not today, not tomorrow, but perhaps in 10 million years. No sound, no explosion, just stone parting from stone. The Red Sea began this way. So did the Atlantic. The irony lies in how continents which seem immense and immovable are in truth the drifting fragments of ancient collisions and ruptures. The map of the earth has never been fixed. It is a record of loss and reunion. Once South America nestled beside Africa. Once Antarctica was not buried in ice but covered in forests joined with Australia. The lines we draw on globes are only moments' pauses in a motion too slow for human senses. Another irony: we measure the drift of these plates not by watching them move but by the tiny echoes of their tension. GPS satellites detect millimeters of shift per year. But more ancient evidence lies in the rocks themselves. Volcanic basalts, as they cool, trap magnetic signals that point to the position of the magnetic pole at the time of their formation. By comparing these signals across continents, scientists trace the paths the continents took, silent trails across 1 billion years. These clues, scattered in lava flows and ocean crust, form a story that requires patience to read. And yet the story remains incomplete. We know the plates move, but the engine of their motion, the precise mechanics of mantle convection, remains partly obscured. How do solid rocks flow so consistently? How do the deepest parts of the mantle interact with the plates above? Are there hidden forces at work we do not yet understand? Some researchers propose that slabs of lithosphere once subducted sink deep into the lower mantle and persist for hundreds of millions of years. Others believe that entire cycles of plate motion creation, drift subduction may begin and end in ways we have not yet observed. These gaps in understanding are not failures but invitations. They remind us that Earth, for all our instruments and models, remains a world of depth and mystery. Beneath the continents lie cratons, ancient cores of continental crust, billions of years old. These keels of stability resist subduction and preserve the memory of Earth's earlier surfaces. In them, zircons older than 4 billion years have been found, tiny crystals that predate the Moon's visible face. These grains, once part of molten rock, now rest in sand and mountain. They have crossed oceans, withstood erosion, and survived metamorphosis, only to be found in riverbeds and outcrops. In a world of change, they are time's fossils, yet even they are not immune. Given enough time, even cratons may rift or collide. The very stones that anchored the first continents may one day melt and return to the mantle. The crust is not an archive, but a manuscript forever being rewritten. Each plate carries a history of collisions, mountains, raised oceans, closed islands, scattered. When two continental plates meet, neither subducts easily. Instead, the land folds, rises, and crumples into towering ranges. The Himalayas, the Alps, the Appalachians, all born from these collisions. But even as mountains rise, erosion works to lower them. Raindrops, ice and wind carry away grains of rock to the sea, undoing in silence what took tectonics tens of millions of years to build. Only took 100 million years to make a range and a few storms to start wearing it down. Beneath this slow violence lies a quiet symmetry. The earth adds and subtracts land with the same hand. Where plates diverge, new crust is born. Where they converge, crust is consumed or uplifted. Nothing is gained without something lost. The cycle is unbroken but never still. This process has no memory. It does not preserve the outlines of past worlds. Pangaea is gone, Rodinia before it, Nuna before that, and yet the continents remember in their rocks. Pieces of ancient shores remain as clues, similar fossils found in rocks now an ocean apart mountain belts that once formed a single range now separated by seas. The continents themselves, once connected, now drift alone. Some will meet again, some never will. The current arrangement of plates is temporary. So too were all those before. This transience gives the earth its beauty, not permanence but motion. In the quiet divide beneath our feet, this motion continues without pause, unseen and unfeeling. Far beneath the waves, beneath the silence of open ocean, lies a spine of fire, a place where the planet opens gently from within. This is the mid-ocean ridge, a continuous seam of volcanic activity encircling the globe, like a quiet scar more than 60,000 kilometers long. It is not a mountain range in the familiar sense, though it rises from the seafloor. It is not violent, though its heat creates new earth. Here, where tectonic plates pull apart, molten rock rises to fill the space. It cools as it touches water, forming fresh basaltic crust. Layer by layer, this oceanic crust spreads outward in both directions, carrying the seafloor with it slowly, endlessly, like a breath drawn over eons. It is a place of constant renewal, though few have ever seen it. The Atlantic Ocean, wide and deep, was born from such a ridge. Its basin grows a few centimeters each year, as the Americas drift west and Europe and Africa drift east. This growth, invisible in the span of human life, reshapes the world all the same. An irony, the ocean floor is younger than the continents it separates. No part of it is older than 200 million years a blink in planetary time. The Earth, 4.5 billion years old, has recycled its seabed many times, erasing its own oldest stories. The continents remember, the oceans forget. As new crust forms at the mid-ocean ridge, it begins a journey away from the heat that gave it life. Cooled, thickened, and burdened with time, it travels slowly across the ocean basin. Eventually it meets its end at the far edges of the plates in the cold trenches of subduction zones. There the heavy oceanic crust bends downward, sliding beneath another plate and sinking into the mantle's slow churn. This cycle of creation and destruction is called seafloor spreading, but the name belies its elegance. It is not spreading so much as breathing a slow exhalation at the ridge, a slow inhalation at the trench. The crust born hot and light dies cold and heavy, and it does so without resistance. At the heart of this process is basalt, the dark, dense rock of the ocean floor. It forms in sheets and pillows as lava cools beneath seawater. It carries with it magnetic minerals which align with Earth's magnetic field at the moment of crystallization. These minerals, primarily magnetite, act like tiny compass needles, freezing in place the direction and polarity of the planet's magnetic field at the time of their formation. The ocean floor then becomes a magnetic tape recorder. As the crust moves away from the ridge, it preserves bands of alternating polarity symmetrical on both sides. These stripes, discovered in the mid-20th century, confirmed what theory had only suggested. They showed that the seafloor was indeed spreading slowly, rhythmically, carrying evidence of magnetic reversals across its surface. Only took a few million years to record a flip. The irony here is gentle. The very process that creates new crust also guarantees its destruction. No part of the ocean floor survives indefinitely. It is born, moves, and is consumed, a geological reincarnation. The continents, by contrast, are less often subducted. They ride higher, less dense than the mantle below, and so they float. They endure. But the oceans live brief if majestic lives. Despite the clarity of this pattern, questions remain. What initiates the upwelling at mid-ocean ridges? Why do some ridges spread faster than others? The East Pacific rise, for example, outpaces the Mid-Atlantic ridge by a wide margin. How deep does the connection go between mantle convection and ridge volcanism? We know that heat drives the system, but the exact architecture of the flow remains partly hidden. The deeper we look, the more complex the picture becomes. Some ridges are offset by fractures called transform faults, where plates slide past each other rather than away. These faults cut the ocean floor into jagged segments, creating earthquake zones in places that otherwise seem quiet. Others host hydrothermal vents, black smokers, where mineral-rich water superheated by magma gushes into the deep sea. Around these vents, life flourishes without sunlight, drawing energy from chemistry alone. Tube worms, clams, and microbial mats thrive here, hinting at how life might have begun on Earth or even elsewhere. A poetic detail in the darkest depths of the ocean life clings to warmth and metal nourished by the breath of the Earth itself. Another irony, the mid-ocean ridge birthplace of crust is also a nursery for alien life. And yet above the surface the ocean gives no hint. The ridges are buried deep beneath kilometers of water invisible from land or ship. Their presence is known only through sonar maps, magnetic anomalies, and the occasional submarine expedition. They are the longest continuous mountain range on Earth, and yet they have no skyline. They rise not into air but into water, silent, unseen, enduring. Scientists once believed the ocean basins were static, their shapes defined at the planet's birth. But in the 20th century, as data from seismology, magnetics, and oceanography accumulated, a new picture emerged. One where the Earth is dynamic, restless, and self-renewing. one where the continents are not eternal but momentary configurations, one where the seafloor is born and devoured in cycles too slow to witness but too vast to ignore. The mid-ocean ridges form the core of this vision. They are not merely features, they are engines. They remind us that Earth is not a finished world but a work in progress, a crust in motion, a surface that shifts. And they teach us that the grandest movements are also the quietest. The ridges do not roar, they do not tremble, they do not rise above the ocean's veil. But they are always there, building the world from the bottom up. Where the ocean's floor descends into darkness, deeper than any trench of memory lies the quiet reversal of creation, the slow disappearance of Earth's crust into the mantle's open arms. These are the subduction zones where one tectonic plate sinks beneath another, returning to the interior what was once born at a distant ridge. It is here at the edges of ocean basins that the Earth closes the loop of its own breath. What rises must fall, what is made must vanish. There is no ceremony, no rupture. The descent is gradual, continuous, as silent as snowfall. As oceanic plates age, they cool and grow dense. Weighted by basalt and time, they become heavy enough to bend downward when they meet lighter continental crust. This meeting does not happen with fury but with pressure, the slow, unceasing push of one mass against another, like glacial ice pressing into stone. The oceanic plate slides beneath the continental, forming a trench at the boundary, and initiating its long journey into the mantle below. The process is vast in scale, yet it unfolds in increments no eye can see. The Mariana Trench, deepest place on Earth, marks such a boundary. The Pacific Plate bends and disappears beneath the smaller Philippine Plate, descending at angles that reach hundreds of kilometers below the surface, and yet above the waves only a crease in the sea marks the boundary. Nothing visible suggests the depth of transformation beneath. An irony, the places where the planet folds in on itself are among the least accessible to human study. At subduction zones, rock becomes memory. The plate's journey downward creates a cascade of effects: earthquakes, mountain chains, volcanic arcs. As water and sediment are dragged into the mantle, they lower the melting point of rock, generating magma. This magma rises to the surface, feeding chains of volcanoes like the Andes, the Cascades, or the volcanic islands of Japan. Destruction therefore gives rise to creation. A plate vanishes and a mountain is born. A trench deepens and an island emerges. Only took 200 million years to sculpt a continent's edge. In this cycle, time serves as both sculptor and eraser. Rock born of fire is returned to it. Oceanic plates among the youngest surfaces on Earth are also the first to die. Their subduction erases them almost completely, not just the physical stone, but the records they hold. The continents, by contrast, do not easily sink. Too buoyant, too thick, they resist subduction, and persist through time, accumulating history in layers of sediment folding into mountains sheltering ancient cratons. While oceanic plates vanish, continents endure a quiet asymmetry in the life cycles of Earth's crust. And yet the boundaries where plates meet are not smooth or predictable. They are jagged zones of tension where the crust locks and then slips, causing earthquakes that ripple across thousands of kilometers. The energy released in seconds may have taken centuries to build. These tremors mark the sudden adjustment of stone under pressure, a fault slipping a slab, shifting a boundary, reasserting itself. Most of the planet's largest earthquakes occur in subduction zones, but even these events, destructive as they may seem to human life, are only flickers in the larger rhythm of tectonics. To the planet, an earthquake is a sigh. Still, some mysteries linger. What triggers the initiation of subduction in the first place? Why do some plates bend easily, while others resist for tens of millions of years? Why do certain subduction zones generate deep earthquakes, hundreds of kilometers beneath the surface, while others remain shallow. Seismologists study the descending slabs through patterns of earthquake waves, tracing their paths like shadows in stone, but the interior remains largely unseen. Some propose that slabs sink all the way to the core mantle boundary before slowly mixing back into the deep mantle. Others suggest they stall midway, suspended like ghosts of vanished oceans. The truth lies somewhere within the Earth's deepest folds, a place beyond reach, inferred only through whispers of motion. Another poetic irony, the stone that crumbles mountains and lifts volcanoes, begins its fall in the quiet cold of the deep sea. Subduction zones are not fixed forever. As plates shift and collide, new subduction zones can form while old ones die. The Mediterranean once held a vast ocean, the Tethys, whose floor was consumed by subduction. Today, only fragments remain caught in the crust of Europe and Asia. The closure of this ancient ocean built the Alps, the Carpathians, the mountains of Turkey and Iran. Oceans close with no sound. Continents rise in their place. The Wilson cycle, the rhythm by which oceans open and close, is tied intimately to subduction. It is a process without haste, without pause. An ocean may take hundreds of millions of years to form and just as long to vanish. In this time, continents travel great distances, spin, split, and merge. Yet to the rocks at a subduction zone, only the moment matters, the slow descent into heat, the transformation of crust into mantle, the quiet end of surface memory. A final irony, the engine that drives the drift of continents and the creation of new land, is not found in the rising of magma or the forming of mountains, but in the sinking of old seafloor. The Earth moves forward by letting go. Subduction is not an act of violence, but of renewal. What disappears beneath one plate may re-emerge elsewhere, transformed, heated, uplifted as a volcano, a mountain, a grain of sand. The journey of the plate does not end, it merely deepens. The mantle beneath the plates, though solid in form, flows with the patience of eternity. It moves not like water, but like honey left in cold air, dense, slow, unhurried. This movement, driven by heat from the Earth's core and by the slow cooling of the planet, forms the great engine of tectonic motion. Here in the asthenosphere, temperatures reach over 300 degrees Celsius, yet pressure is so immense that rock behaves like an extremely viscous fluid. Convection currents, invisible but persistent, ripple through this layer, rising where it is hot and buoyant, sinking where it is cooler and denser. Over millions of years, this circulation drags the overlying plates along with it, sometimes pulling them apart, sometimes pushing them into one another. The mechanism is simple, but its consequences shape worlds. Heat moves from the interior to the surface as it must. This heat, a remnant of the planet's formation, and the decay of radioactive elements, drives a system without pause. Rising plumes of hot mantle material known as upwellings can lead to rifting, creating mid-ocean ridges or continental breakup. Meanwhile, cold, dense lithosphere that descends into the mantle pulls the plate behind it in a process known as slab pull. Ridge push, another force, results from the elevation difference between spreading centers and the rest of the plate. These forces, together subtle and immense, dictate the paths of continents and the fate of oceans. Only took a few billion years for the Earth to find its rhythm. Yet despite our understanding of these broad principles, much remains uncertain. The mantle cannot be observed directly. Its behaviors are modeled through seismic wave studies, high-pressure experiments, and computer simulations. What lies within it is glimpsed only in fragments, pieces of mantle rock brought to the surface by volcanic eruptions or the shifting signals of deep earthquakes. Some regions, known as mantle plumes, may rise from near the core mantle boundary, bringing heat and material from the deepest parts of the Earth toward the lithosphere. These plumes are believed to feed hotspots locations like Hawaii or Iceland, where volcanism occurs far from any plate boundary. The idea of these plumes towering columns of rising rock remains controversial in its details, but the fingerprints of their presence are found in the islands they create. An irony, a single column of heated rock rising imperceptibly through the mantle over tens of millions of years can give birth to an archipelago, a chain of volcanoes stretching across an ocean. The earth, through warmth alone, sculpts beauty, and yet this heat is not evenly distributed. The mantle flows differently in different regions. Some areas show signs of faster convection, others of stasis. Large low-shear velocity provinces, immense blobs of different composition and temperature appear to sit near the base of the mantle, perhaps remnants of ancient subducted slabs or chemically distinct domains from early Earth. Their origin remains mysterious. Do they represent buried continents, recycled crust, deep mantle anomalies formed shortly after the Earth's birth? The question lingers heavy and unresolved. The mantle, it seems, does not forget, and neither does it repeat itself exactly. While convection cycles have likely occurred since Earth's early history, their patterns may have changed. In the Archean eon, when the Earth was hotter, convection may have been more vigorous, the plates smaller and more numerous. Some scientists believe that plate tectonics itself began gradually, perhaps not starting in full until 2 to 3 billion years ago. Before that, the Earth may have experienced different styles of internal motion: heat pipe volcanism, stagnant lid convection, episodic overturns. In other words, the surface may have rested under different regimes of geological breath. Only took half the planet's lifetime to settle on its current mode. The fact that we live in an age of global tectonic motion may not be permanent. As the Earth cools further, plate tectonics may slow or cease. The system is driven by internal heat, and as that heat declines, so too may the vigour of the mantle's flow. In the far future, continents might freeze into place, mountains cease to rise, and the ocean basins become fixed. But for now, the system moves, and in doing so, it creates the land beneath our feet, the mountains that catch clouds, the deep trenches that swallow old seafloor. A poetic detail, the movement of the mantle, measured in centimetres per year, is responsible for the height of Everest, the drift of Australia, the slow closure of the Pacific Ocean. The softest force becomes the shaper of all. Another quiet irony, the mantle's flow, though mechanical and blind, gives rise to the Earth's surface variety, not from intention, but from interaction. It is the contrast between heat and cold buoyancy, and density rising and sinking, that creates continents, oceans, rift valleys, and volcanic arcs. The surface dances to a rhythm it cannot hear. Even earthquakes and volcanoes, those sudden acts of geologic release, are merely expressions of the slow dance beneath. The real motion, the true driving force, lies deeper, and it is unbroken. Yet we are left with questions. What initiates changes in convection patterns? Why do some plumes persist for hundreds of millions of years while others fade? How connected is the surface motion to the deep interior? The mantle structure is layered, complex, and non-uniform. Seismic tomography reveals features like slabs, plumes, and hidden reservoirs. But these images are grainy, limited by resolution and assumption. The deeper we look, the more the image blurs. Still, the mantle flows. It does not wait for us to understand. It teaches through consequence. It gives no answers, only motion. It is the ocean of stone upon which the lithosphere sails. It is the unseen current beneath the Earth's skin. It is the breath of the planet drawn so slowly that even time forgets. When plates collide, the Earth folds upon itself. What was once flat becomes crumpled. Layers of sediment accumulated quietly over eons in shallow seas are lifted, tilted, and thrust skyward into the chill of higher altitudes. These are the mountain belts, the slow consequence of continental convergence, where land presses against land with the force of entire plates. It is not the speed of impact that shapes the peaks, but the duration. A continent moves no faster than a fingernail grows, yet its steady insistence leaves no stone unchanged. The Himalayas' tallest mountains on Earth began to rise when the Indian plate drifted northward and collided with the Eurasian plate. That movement began more than 50 million years ago, and it continues still. Each year the Indian plate pushes a few centimeters farther under Eurasia, lifting the Tibetan plateau ever so slightly higher. The motion is imperceptible, but the mountains it forms are not. They tower not in defiance, but in submission, built from layers that once lay beneath ancient seas. This is how the Earth stores time, not only in the drift of plates, but in the folding of sediments, in the uplift of seabed into sky. An irony, the shells of long-dead marine creatures now rest in limestone high above the clouds. Another irony, the highest points on the planet are made of rock that once lay beneath some of the lowest. Mountain building or orogeny is not limited to one region. Throughout Earth's history, collisions have formed vast ranges, the Alps, the Rockies, the Urals, the Appalachians. Each range is a scar, a memory of plates that once met and never truly parted. In some places, the record of these collisions has been eroded, folded again, or buried. But deep within the crust, seismic waves still travel differently through ancient routes, echoes of mountains long since worn to hills. Folding is only part of the process. As crust thickens, it also delaminates, flows sideways, or breaks into faults. Massive slabs of rock are stacked atop one another like shuffled pages in a book. The scale is immense. A single thrust fault can span hundreds of kilometers. But none of this is sudden. Mountains grow in silence. There are no loud beginnings, only slow pressure repeated endlessly. And just as the Earth raises these peaks, so too does it bring them down. Erosion begins almost as soon as uplift does. Rain, wind, frost, and gravity work slowly to reduce mountains to rubble. Rivers carve valleys. Glaciers grind ridges. Sediments are carried to the sea, deposited in basins, compacted into new rock, and the cycle begins again. What rises must fall, and what falls may one day rise again. Only took a few tens of millions of years to build a range, and only a few more to wear it to the bone. The irony lies in permanence imagined and lost. Even Everest, despite its grandeur, is temporary. Despite our instinct to call mountains eternal, geology does not agree. Beneath these ranges, deep within the crust, pressure and heat cause rock to metamorphose. Limestone becomes marble, shale becomes slate, granite shears and recrystallizes. These changes do not erase the history of the rock, but rewrite it a palimpsest of deep time. Geologists read these transformations to understand the forces that shaped them. Folds, faults, and mineral assemblages become the language of collision. But like any language, much is lost in translation. How exactly did a range form? In what order did faults develop? What temperatures and pressures were reached? These are questions with partial answers stitched together from fragments. Mountain belts offer grandeur but not always clarity. Still, the story they tell is unmistakable. Continents are not fixed shapes but malleable. They stretch, compress, and thicken. The crust itself, though brittle at the surface, flows like wax at depth. It can buckle, it can flow, it can rupture and heal. Beneath the ranges, we see roots extend deep into the mantle-thickened zones of the lithosphere that anchor the surface above. These roots, sometimes 2 or 3 times deeper than the surrounding crust, are part of what gives mountains their lasting presence. And yet even these roots are eventually eroded from below, thinned by the slow dripping of lithosphere into the asthenosphere. Another quiet irony: mountains are worn down not only from above but from within. The earth reshapes itself in both directions. There is no firm bottom to a mountain, only zones of transition, and no clear end to its formation, only a tapering of motion. In some cases, what begins as mountain building may end as rifting. If compression gives way to extension, ranges may become valleys. The crust once thickened may stretch and thin again, reversing what took millions of years to build. The Basin and Range province in western North America is such a place, a region of once raised crust now slowly pulling apart. Faults dip in alternating directions. Valleys sink between uplifted blocks. The record of earlier uplift remains in isolated ranges now stranded like islands in a sea of slow collapse. A poetic detail, the Earth's surface carries both the memory of rising and the gesture of retreat, often layered atop one another. Mountains tell of collisions past, but also of what may come next. Another irony then: the moment a mountain forms is also the beginning of its disappearance. Erosion starts with the first uplift. Subduction may halt, transform faults, may change direction, or the driving forces beneath the plates may weaken. Over time, even the most majestic peaks return to the sea as grains of sand. But in those grains, the record of tectonic history remains. Quartz crystals that once gleamed in alpine cliffs now glitter on riverbeds and coastlines. Stones that stood tall become the foundations of future lands. In this way, mountain belts are both monuments and messengers, not symbols of permanence but of process. They remind us that even the loftiest achievements of stone are born in pressure, shaped by resistance, and destined to fade. And still the earth presses onward. Continents, though vast and seemingly anchored in place, carry within their bedrock the signatures of ancient migrations. Locked inside layers of cooling lava and deep crustal formations are records of the Earth's magnetic past, paleomagnetic clues that whisper of latitudes long since left behind. As molten rock cools, its magnetic minerals, especially magnetite, align with the Earth's magnetic field like silent compasses. Once solidified, they hold that direction in stone, frozen in time. By analysing the orientation of these minerals in rocks of known age, geophysicists can trace the movement of entire landmasses across the surface of the planet. What emerges is a quiet choreography: continents shifting across climate zones, crossing the equator, rotating, slowly drifting toward or away from poles. This magnetic memory gives shape to what the eye cannot see: the wanderings of continents over hundreds of millions of years. Only took 1 billion years to cross a hemisphere, yet paleomagnetism offers more than just a direction. It tells of reversals. The Earth's magnetic field does not remain fixed. Throughout geologic history it has flipped: north becomes south, and south becomes north. These geomagnetic reversals are recorded in the alternating magnetic stripes of the ocean floor and in the rocks of ancient continents. They happen irregularly, sometimes every few 100,000 years, sometimes with gaps spanning millions. The cause remains a subject of study. The movement of molten iron in the outer core likely drives the field, but why it reverses, how long it takes, and what effects it has at the surface remain questions with no firm answers. These flips, though, invisible to early humans and to most creatures, are among the most planetary of phenomena. A poetic detail: the poles have switched so often that the Earth itself seems undecided. Another irony: while these reversals seem chaotic, they are among the most precise clocks in geology. Radiometric dating combined with a magnetic signature of rocks allows scientists to construct detailed timelines of continental drift, to reconstruct past positions, to map vanished oceans, to restore the face of Earth across eons. These reconstructions reveal patterns of ancient supercontinents, land masses that formed and broke apart long before the familiar outlines of modern continents emerged. Rodinia assembled nearly 1 billion years ago, brought together fragments that would one day become North America, Siberia, Australia, and others. Later came Pangaea, and then the most famous of them all, Pangaea. Formed about 335 million years ago, Pangaea was a near-complete assembly of Earth's continental crust, surrounded by a vast global ocean called Pangaea. In this moment of closeness, deserts stretched across its interior and mountain ranges, including the ancestors of the Appalachians and Urals, rose from the pressures of collision. But like all things in tectonics, Pangaea was temporary. It began to rift apart roughly 175 million years ago, its fragments carried by the slow movements of the underlying plates. Today's Atlantic Ocean traces the line of that rupture. The irony is gentle: what once held together now defines what separates. The continents we know, Africa, Asia, the Americas, are not independent creations, but pieces of prior wholes. Each carries on its flanks the scars of past unions, matching rock formations, mirrored mountain ranges, and fossil distributions that ignore modern shorelines. Fossils of the extinct reptile Mesosaurus, for instance, appear in both South America and Africa, a creature that could not have swum an ocean, yet lived across lands that were once joined. These biological traces confirm the paleomagnetic and geological ones. The Earth does not keep secrets. It simply requires time to read, and yet uncertainties remain. Exactly how and when did Rodinia assemble? What caused its breakup? How many supercontinents preceded it? The answers lie in rocks that have been buried, metamorphosed, or destroyed. The deeper into time we reach, the blurrier the picture becomes. Some models suggest a cycle, a supercontinent every 500 to 700 million years, the so-called supercontinent cycle. Yet the details vary. Reconstructions become speculative, fragmentary. Another poetic irony: the closer we get to the origins of the Earth's surface, the less clearly we can see. Still, the story is one of motion, of drift, of reunion and separation. A quiet planetary heartbeat. In the present, the continents continue to move. North America shifts westward toward the Pacific. Africa migrates slowly north, closing the Mediterranean. Australia races northeast, headed toward Asia. These movements are imperceptible day by day, but become significant over millions of years. Given enough time, another supercontinent will form. Scientists have named this possible future mass Pangaea Proxima, or Amasia, depending on its predicted structure. But the exact arrangement remains unknown, as does the timing. Predictions suggest 200 to 300 million years in the future. The surface of the Earth will be different. Oceans may vanish. Mountains will rise in new places. And then, as before, it will all break apart again. Only took 500 million years to reunite the fragments. Another irony: each supercontinent begins with collision and ends with rupture. The strength of union contains the seed of its own undoing. Heat builds beneath the insulating mass. Tension grows at the seams. Eventually the crust splits and the cycle begins anew. Through paleomagnetism, radiometric dating, and the careful reading of rock, we glimpse these vast movements not as stories but as records. There are no characters, no climaxes, no resolutions. Just slow change, just drift, just stone moved by time. The continents wander not from aimlessness, but from the quiet persistence of mantle flow. They rotate, rearrange, sometimes overlap. A continent that once lay near the South Pole may one day circle the equator. The planet offers no fixed home, only the rhythm of motion. Before Pangaea, before even Rodinia, Earth's continents gathered and parted in cycles now nearly erased. The deeper into time we peer, the fewer the clues, yet the patterns persist. Supercontinents form not as singular events, but as recurring phenomena, slow reunions of drifting fragments pulled together by the inevitable closure of oceans. These ancient assemblies are not mere arrangements of land, but expressions of the mantle's breadth of forces that lie far beneath the surface. The names Nuna Columbia Kenorland Ear are modern constructions, attempts to grasp at the long-vanished shapes of land masses whose rocks remain but whose outlines have faded. These were not static formations. They were born from collision endured by compression and undone by the same slow rifting that built the oceans. Each supercontinent tells a variation of the same story. Fragments coalesce, join under pressure, form mountain belts, and then fracture apart, sometimes along the same scars they once healed. Only took 1 billion years to forget how they fit together. The process of assembly begins with subduction. As oceanic plates dive beneath others, continents are drawn together. Island arcs collide, mountain ranges rise, sutures form in the crust. Over time, these collisions aggregate into larger masses. The driving force is the closure of ocean basins, the inverse of seafloor, spreading, a process just as slow, just as certain. Eventually enough fragments meet to form a new supercontinent. But once assembled, the vast landmass alters the dynamics of heat flow beneath it. The thick lithosphere insulates the mantle, causing heat to accumulate. Mantle plumes, once dispersed, may focus beneath the supercontinent's center. Tension builds from below, stretching the crust, weakening it until rifts open, and the land breaks apart once more. The irony is gentle. What unites must eventually fracture, and the center often fails first. The breakup of Pangaea followed this pattern. Around 200 million years ago, rifts opened between what is now North America and Africa. These rifts became the Atlantic Ocean, and the continents drifted away on newborn plates. The record of this breakup remains in the geology of passive margins, coastlines that once bordered active rifts. Sedimentary basins, flood basalts, and fault zones all point to the slow expansion of ocean, where land once met land. The continents did not tear violently, but eased apart over tens of millions of years. Another irony, the gentle pull of mantle flow can sever what collisions once welded shut. The supercontinent cycle is not exact, but it is enduring. While the names and configurations vary, the rhythm of assembly and breakup has repeated at least 3 times, perhaps more. Each cycle reshapes climate, biodiversity, and ocean circulation. When continents cluster near the equator, weathering increases, drawing carbon dioxide from the atmosphere and cooling the planet. When they gather near the poles, glaciation becomes more likely. The position of land affects wind current and life, not by design but by consequence. Supercontinents influence extinction and evolution not with purpose but with presence. A poetic detail, the very ground beneath our feet once travelled together as a single colossal island surrounded by a limitless sea. The oceans too change with the supercontinent cycle. When all land is gathered, only one vast ocean surrounds it. Panthalas are earlier equivalents. These global oceans are deep, wide, and relatively featureless. But as rifting begins, new basins form smaller seas enclosed by drifting continents. The Tethys Ocean, for instance, formed between Laurasia and Gondwana after the initial breakup of Pangaea. It later vanished, consumed by subduction beneath Eurasia, leaving behind only the Mediterranean as a fragment of its once vast reach. Another irony, today's inland seas are not new, but remnants, echoes of vanished oceans trapped between drifting shores. The supercontinent cycle leaves lasting marks on Earth's crust. Suture zones where plates once collided often host rich mineral deposits. The compression, heat, and fluid movement associated with mountain building concentrate metals like gold, copper, and lead. Ancient mountain belts, long eroded, may no longer rise into the sky, but they remain vital to human economies, offering resources hidden in the deep roots of collisions past. In this way, even the forgotten joins of ancient continents continue to shape the present. Still, the details of these ancient cycles remain elusive. The further back in time, the less intact the record. Rocks have been metamorphosed, subducted, melted, or eroded. The continents we now see carry only fragments of their earlier lives. Reconstructing past configurations requires a patchwork of clues matching rock types, fossil distributions, paleomagnetic data, and isotopic signatures. These reconstructions are not static. New data reshapes them, shifts the boundaries, redraws the connections. Another quiet irony. The ancient past is less settled than the present. Even now, geologists debate the order and timing of supercontinent cycles. Did Nuna come before Columbia, or are they two names for the same assembly? Was Ur a full continent, or merely a craton? How many times has the Earth gathered its lands into one? How many more will come? These questions remain open, not because the answers are unknowable, but because they are deeply buried not just beneath sediment and stone, but beneath uncertainty. Still, the broad pattern endures. Earth has not always looked like it does today, nor will it remain this way. The continents are travellers meeting and parting again and again in cycles older than fossils, older than the air we breathe. Each reunion builds mountains, each separation opens seas. A supercontinent may hold deserts, glaciers, rainforests, and swamps, all within a single landmass. Then, as it fragments, the pieces scatter, carrying climates and species, with them isolating populations, driving evolution. What seems like geological motion becomes biological transformation. Life and land move together. The continents remember not with words but with stone. Oceans, like continents, are not permanent fixtures. They appear, widen and vanish according to the slow logic of plate motion, a rhythm not of tides but of crust. The story of any given ocean is one of birth, by rifting growth, by spreading and eventual closure through subduction. This cycle, known as the Wilson cycle, governs the life of ocean basins across hundreds of millions of years. It is named not for mythology, but for geophysicist J. Tuzo Wilson, who first recognized that ocean basins follow a pattern of renewal and erasure. Each sea that exists today is somewhere along that trajectory. Some are young and widening, others mature, and still others are in decline. None will remain as it is. Only took a few 100 million years to open the Atlantic. It will take just as long to close it again. The Wilson cycle begins with rifting. As continental plates stretch and thin, the lithosphere fractures and magma wells up from the mantle. This process begins quietly, a few faults, some volcanic activity, the gradual formation of a rift valley. If rifting continues, the valley deepens and widens until it fills with water, becoming a narrow sea. With time and further spreading, it grows into a full-fledged ocean basin. The Red Sea, for example, marks a nascent ocean, its edges diverging its floor, forming new basaltic crust, its waters slowly expanding. Should this continue, it may one day match the scale of the Atlantic. But the process is unhurried. Seafloor spreading adds just a few centimeters per year. The Atlantic Ocean itself began this way, when Pangaea ruptured during the Mesozoic era. What is now the eastern coast of South America once fit neatly against the bulge of West Africa. The rift that began between them widened into a basin flooded by seawater and has been growing ever since. Magnetic stripes on the ocean floor, symmetrical parallel bands, recording geomagnetic reversals, chart this expansion with quiet precision. But growth is not the ocean's only fate. Eventually, as plates continue to shift, subduction begins along the margins. One plate bearing the oceanic crust bends and slides beneath another. A trench forms then a volcanic arc. The basin begins to narrow. This is the closing phase of the Wilson cycle. The Pacific Ocean, broad and ancient, may now be in such a phase. Subduction zones ring its edges, the so-called ring of fire, consuming oceanic crust at multiple boundaries. Though it still spans more than a third of the globe, it is shrinking slowly, its days measured not in waves but in mantle pull. Another irony, the deepest parts of the world are also the most temporary. Over time, as the ocean closes, continents move toward collision. The basin narrows further. Island arcs and microcontinents may be caught in the squeeze plastered onto larger landmasses. Eventually, the last remnants of ocean are consumed and the continents collide fully. The result is orogeny mountain building on a continental scale. The Himalayas rose from such a collision, but so did the Appalachians and the Urals. Each marks the site of a vanished sea. A poetic detail, every mountain range on a continent may be the tombstone of an ancient ocean. Yet not all collisions are straightforward. Sometimes pieces of seafloor are scraped off and accreted to the continental edge. Other times, oceanic plateaus, seamounts, and volcanic arcs are jammed into the collision zone. These fragments, called terranes, carry with them rocks and fossils foreign to the continents they join. The western edge of North America is stitched from such pieces, a collage of crust drifting into place from distant realms. Another irony, the edges of continents are often not their own. The Wilson cycle is not a precise clock. Oceans may exist for varying lengths of time. The Iapetus Ocean, which preceded the Atlantic, lasted about 200 million years. The Tethys Ocean, caught between Gondwana and Laurasia, endured through much of the Mesozoic before vanishing beneath Eurasia. Its memory lingers in the rocks of the Alps, the Zagros, the Himalayas. The Mediterranean is what remains a sliver of a vanished sea. Today the Atlantic still grows, but evidence suggests it too will eventually reverse. In some models, a new subduction zone may form off its eastern edge. Perhaps in 200 million years, as Africa collides with Europe and the Americas drift eastward, the Atlantic will close and a new supercontinent will form. The outlines are speculative. The motion is certain. The opening and closing of oceans reshapes not just geography but climate. Ocean currents change with basin geometry. Seaways can isolate or connect entire ecosystems. The closure of the Isthmus of Panama, for example, altered Atlantic and Pacific circulation and played a role in Pleistocene glaciations. Tectonics, though, slow rewrites the Earth's climate one collision at a time, and beneath these physical changes lies a deeper mystery. Why does the Wilson cycle occur at all? Why do continents come together, then part only to return? The mantle flows, the plates move, but why in patterns? Why in recurrence? Is it geometry or thermodynamics? Is it chance or necessity? These questions remain open. What is known is that the Earth through this cycle continually renews itself. Crust is created and destroyed. Oceans open and close. Continents migrate, fracture and reunite. There is no final configuration, only drift. The Wilson cycle is not a law but a pattern. It may be broken, altered or changed, but for now it endures a quiet pulse through geologic time. Even where plates do not collide or pull apart, they can still grind past one another with immense silent force. These are the transform boundary zones of lateral motion, where two tectonic plates slide horizontally along a shared fault line. There is no creation of new crust here, no subduction of old. The plates remain on the surface side by side, locked in friction, shifting inch by inch, year by year, until the pressure becomes too much to bear. Then, in a single sudden motion, decades or centuries of tension are released. The ground trembles. A line of weakness becomes a flashpoint, and then it is still again. The San Andreas Fault is perhaps the most well-known of these zones, where the Pacific Plate and the North American Plate grind past each other along the spine of California. The movement is slow, a few centimeters per year, yet over centuries it accumulates into kilometers. Faults do not cut through the crust cleanly. They are complex zones of shattered rock, sometimes hundreds of meters wide, marked by past earthquakes, and filled with deformed minerals. These transform faults may link other plate boundaries, connecting spreading ridges across the ocean floor or acting as boundaries between major land masses. Some extend for thousands of kilometers. Others are short but deep hidden beneath the sea. In all cases, they are reminders that the Earth does not always pull or push, sometimes it shears. A poetic detail on either side of a transform fault, the world moves in different directions silently, like dancers facing away from each other, bound by a shared rhythm they do not acknowledge. The friction along these faults builds over time, as the plates press against one another, locked by the irregularities of their surfaces. Elastic energy accumulates in the surrounding crust. When the frictional resistance is overcome, this energy is released as an earthquake. The magnitude depends on the length of the fault, the depth of rupture, and the amount of stored stress. Most of the motion happens in moments, but the deformation and aftershocks can persist for weeks. Only took a century to prepare. Only took 30 seconds to release. Yet even in these sudden events, the broader tectonic movement continues without pause. Transform boundaries remind us that the Earth is not a passive surface, but a system of interacting blocks, each with its own path and momentum. Unlike convergent or divergent boundaries, transform faults often leave little topographic trace. Some are buried beneath cities, rivers, or forests. Others lie beneath the ocean, visible only through seismic mapping. Their presence is known more by their effects than their form. Earthquakes, surface ruptures, offset streams, these are the signatures of sideways motion. Another irony, the quietest-looking land may hide the most restless foundations. These faults also reveal how imperfect the boundaries between plates truly are. They are not simple lines, but zones of deformation. Blocks rotate, microplates emerge, and the crust becomes fragmented into a mosaic of rigid and semi-rigid pieces. In some regions, transform motion spreads across dozens of smaller faults. In others, it is focused into a single strand. The boundary is dynamic, changing over time as stress redistributes. Some transform faults, accommodate motion for tens of millions of years before shifting location or dying altogether. The trace remains in the rocks, but the function moves on. At mid-ocean, ridges transform. Faults connect segments of spreading centers, creating a jagged stair-step pattern across the ocean floor. Here the motion is between newly formed basaltic crusts sliding side by side. These oceanic transform faults can be hundreds of kilometers long and extend deep into the lithosphere. Despite their remote location, they are among the most active seismic zones on the planet. Seismic waves from these underwater faults ripple silently across the globe, sensed only by instruments. No one hears them, but they continue. Transform boundaries also shape landscapes in subtle ways. Valleys may form along them. Rivers may be deflected. Mountains may shift laterally. Over long timescales, these movements accumulate into significant offsets. In California, geological evidence shows that the San Andreas Fault has displaced streams and rock units by more than 500 kilometers over the past 30 million years. The land itself slides past itself, leaving a record in dislocated mountains and torn sediments. Still, the causes of fault initiation are not always clear. Why does a plate boundary evolve into a transform fault rather than another type? What controls the distribution of motion across multiple strands? How do faults nucleate, and how do they die? These remain open questions investigated through field mapping, seismic monitoring, and computational modeling. The deeper the fault, the more elusive its workings. We observe the motion, but the mechanism remains partially obscured. A quiet irony, some of the most studied features on Earth are still the least understood. Faults also evolve. New ones can form as plate directions change. Old ones can become inactive, locked forever in rock. Some faults remain aseismic, moving in slow, creeping shifts without quakes. Others remain locked for centuries before a sudden rupture. These differences stem from rock-type fluid pressure temperature and stress orientation, a delicate balance in a deep dark world. The variability is endless. The principles are simple. Transform faults, though less visually dramatic than subduction zones or rift valleys, are essential to the tectonic puzzle. They allow the plates to adjust their positions without necessarily creating or destroying crust. They accommodate differences in direction and rate of motion, relieving stress that would otherwise distort the plates. They complete the network of boundaries that makes plate tectonics possible, and they do so quietly, without eruption, without uplift, often without notice. Another poetic detail: the Earth's largest shifts sometimes come not from the force of collision, but from the quiet persistence of sliding past. The world we see moves laterally beneath our feet unnoticed until it doesn't. Then briefly we remember the fault. Then silence returns. Some pieces of Earth's crust do not drift across oceans or form mountain chains. Instead, they vanish entirely, pulled downward into the deep mantle and lost to time. These are the remnants of subducted plate slabs of lithosphere that once floated at the surface, now sinking through the planet's interior in a journey that may last hundreds of millions of years. Their descent is slow but unstoppable, driven by the cold density of ancient oceanic crust sliding beneath younger, warmer plates. Once subduction begins, the slab detaches from the surface and begins to fold into the mantle like a ribbon of stone, disappearing from view and from most instruments. Yet their presence lingers, detectable only in the subtle signatures they leave behind: cold anomalies in seismic tomography, ghostly traces deep within the Earth. These sunken slabs form what scientists call slab graveyards, vast regions at the base of the mantle where old crust accumulates in layers crumpled and compressed by the weight of eons. In these graveyards, the oceanic lithosphere, once part of the Earth's skin, becomes part of its hidden core. Only took 200 million years to cross a basin. Only took a few more to fall beyond return. The fate of these slabs remains a subject of quiet mystery. Some models suggest they reach the core mantle boundary, flattening into dense piles above the liquid outer core. Others propose that they stall in the mid-mantle, held in place by differences in composition or changes in viscosity. The truth is layered. Some slabs descend all the way, others dissolve or mix partway down. The mantle is not uniform. It is a complex convective system influenced by temperature, mineral phase transitions, and subtle chemical differences inherited from early Earth. Slabs contribute to this complexity. As they descend, they carry water sediments and crustal material deep into the mantle, introducing heterogeneity into a realm once thought homogeneous. A poetic detail: what falls into the Earth does not vanish. It becomes part of the next breath, the next plume, the next basalt plane. In this way, the planet recycles not only rock but memory. Seismic tomography, the imaging of the Earth's interior using earthquake waves, has revealed these slab-like structures with increasing clarity. As seismic waves pass through the Earth, they speed up in colder, denser regions. These anomalies trace the descent of subducted plates, outlining their shape as they plunge downward. Some are steep and narrow, others broad and curved. Their geometry records the history of motion at the surface. A subduction zone that operated for hundreds of millions of years may leave a deep linear slab reaching from crust to core. Others, more recent or intermittent, leave shallower traces. Yet even with these tools, much remains obscured. The resolution of seismic data decreases with depth. The mantle is vast and secretive. Only with the quiet accumulation of data from thousands of earthquakes over decades can a coherent picture begin to emerge. Another irony: the deepest, most ancient structures on Earth are reconstructed from the briefest, most ephemeral vibrations. Slabs influence mantle flow. As they descend, they may drag material with them, generating return currents that help drive plate motion. Their sinking can alter the convection patterns that control volcanism and heat flow. In some models, slabs reaching the core mantle boundary may trigger upwellings of hot material mantle plumes that eventually form surface hotspots. Thus, what goes down may in time call something back up. A subducted plate beneath the Pacific may help initiate a plume that creates islands in the Indian Ocean. Cause and effect drift apart in space and time. The process is global, indirect, and slow, but connected. Some subducted slabs are so old they correspond to oceans that no longer exist. The Farallon Plate, once an immense oceanic plate between North America and the Pacific, has been almost entirely consumed. Its remnants lie beneath the western United States, forming a complex jumble of cold material in the upper and lower mantle. Parts of it are thought to influence volcanism and seismicity across North America even now, long after the plate itself vanished from the surface. A poetic irony, the ground we walk on may still respond to the ghost of an ocean floor last seen in the Jurassic. And yet slabs are not indestructible. As they descend, they undergo transformations. The high pressures and temperatures of the mantle cause mineral structures to change. Water released from hydrated minerals can trigger partial melting, creating magmas that rise to feed volcanic arcs. With time, the slabs become less distinct, mixing into the surrounding mantle. Their boundaries blur. Their identity fades. Eventually, they are no longer separate features, but part of the planet's deeper convection, indistinguishable from the rock around them. Another quiet irony even stone forgets if given long enough. In this way, Earth renews itself. The cycle of plates is not only one of surface drift, but of internal exchange. Crust becomes mantle, mantle becomes crust. Materials rise, fall, and rise again. There is no true disappearance, only transformation. Subducted slabs, though buried and lost to vision, remain essential to the Earth's engine. They pull plates forward, shape mantle currents, and recycle the chemistry of the crust. Without them, the surface would stagnate. Continents would cease to move. Volcanism would slow. The entire system depends on this quiet descent, and still the details remain elusive. What controls the angle of subduction? Why do some slabs penetrate deep while others flatten out? What happens to the sediments and water they carry? Are they preserved, melted, or mixed? Each slab writes its own chapter, and each chapter ends in silence. The world above forgets, but deep below the planet remembers. Though we call the mantle solid, it flows. Not in torrents or surges, but in a creeping drift. The movement of stone over spans of time so vast that the distinction between fluid and rock begins to blur. This flow underlies everything: the drift of continents, the rise of mountains, the opening and closing of oceans. It is the quiet machinery of a planet always in motion. Yet this flow is not uniform. It varies with depth, with temperature, with composition. The upper mantle, particularly the asthenosphere, behaves like a very viscous fluid deforming under stress. Here the rocks yield over geologic time, enabling tectonic plates to glide above. The deeper mantle, denser and hotter, moves more slowly still, but it moves nonetheless, responding to the same imperatives of heat and density that drive all convection. Heat from the core radiates outward. Cooler, heavier material sinks. In between, the rock responds with a kind of stiffness softened by time. It flows not because it is soft, but because the pressures are enormous and the timescales long. Only took 1 billion years to turn a solid into a current. This mantle flow is responsible for the slow churning of the Earth's interior. Convection cells rise and fall. Some are broad and shallow, operating in the upper mantle. Others extend from the core mantle boundary to the base of the lithosphere. These cells are not perfect circles. They are stretched, diverted and deformed by slabs descending into them and plumes rising through them. The mantle is not a still pool but a restless, slow-moving sea of stone. Its patterns resemble the eddies in a pot of simmering soup, except that each swirl lasts millions of years. Seismic tomography offers a glimpse into these patterns. It reveals zones where seismic waves travel more quickly, colder, denser regions likely associated with subducted slabs, and zones where they travel more slowly, hotter, possibly upwelling material. These slow anomalies may mark the roots of mantle, plumes, columns of heated rock rising toward the surface from great depths. The existence of these plumes is supported by surface expressions, volcanic hotspots that remain fixed while plates drift overhead. Hawaii, Iceland, Yellowstone each stands above a suspected plume. The lavas here are chemically distinct, drawing from deep sources not typically accessed by mid-ocean ridges or subduction zones. A poetic detail, some volcanic islands are the breathmarks of the deep earth tracing lines across oceans as the crust floats by. The chemistry of erupted basalt also tells us about mantle flow. Trace elements and isotopic ratios can reveal whether the source is primordial unchanged since Earth's early history, or recycled made from subducted crust that has been processed and returned. The mantle, then, is both ancient and renewed, a blend of untouched reservoirs and well-travelled materials. It carries within it the memory of early Earth and the constant mixing of modern tectonics. Another irony, what seems uniform from the outside, is composed of fragments, a mosaic of origins moving together through time. Yet despite this motion, the mantle retains structure. Its behaviour changes across depth. Near the surface it is cooler and more viscous. Below 66 kilometres, a transition zone marks a shift in mineral structures altering how the rock flows. Deeper still, near 900 kilometres, the core mantle boundary presents a new regime. Here, extreme heat and pressure may give rise to partially molten regions, complex phase changes and the birth of mantle plumes. This boundary is not smooth. It is rough, jagged and variable. It may even contain chemically distinct materials, remnants of ancient collisions or the residues of long recycled slabs. These structures, known as large low shear velocity provinces LLSVPs, are dense and hot. Their role is debated. Some think they anchor plumes. Others suggest they are leftover fragments from early Earth differentiation. Either way, they contribute to the complexity of mantle flow. Not all movement is vertical. Lateral flow within the mantle can carry material thousands of kilometres horizontally. This lateral transport affects the distribution of heat and the positioning of tectonic features at the surface. It explains why hotspots may drift, or why volcanism can occur far from obvious plate boundaries. The Earth is not layered like a cake, but stirred like batter, slow, deep and imperfect. Despite this complexity, the mantle remains largely out of reach. Our deepest boreholes barely scratch the crust. The mantle must be studied indirectly through seismic waves, xenoliths carried up by volcanic eruptions and experimental simulations of high pressure. These windows are narrow, but they yield insights. Some xenoliths contain garnet, olivine and pyroxene minerals stable only at great depths. Others bear isotopic signatures that hint at deep mantle reservoirs. From these clues we piece together a story of motion without rest. A poetic irony, we know the deep earth best by what it offers up to the surface. Tiny fragments brought up violently, then studied patiently. The mantle's flow drives plate tectonics, but plate tectonics also affects the mantle. Slabs that descend pull mantle material behind them. Rifting plates draw mantle upward to fill the gap. The system is coupled. The lithosphere and mantle are not separate actors, but interdependent parts of a single dynamic. As plates move, they reorganize mantle circulation. As mantle flow evolves, it alters the paths and speeds of plates. There is no hierarchy, only exchange. Another irony: the slowest parts of the planet are the ones that shape it most. What takes eons to shift can lift continents drown. Oceans build mountains and end them again. Still we ask, will the mantle always flow? As Earth cools, its internal heat budget diminishes. The vigour of convection may decline. The plates may slow. One day perhaps they may stop. The planet may enter a stagnant lid phase like Mars or the Moon. But that future remains distant. For now the mantle continues to breathe. Its flow is soft, continuous, ancient. It holds no urgency. It forgets nothing, it waits for nothing. Across the face of the planet there are places where the pace of drift becomes visible, where collision is no longer hypothetical, and where geology breathes through the rise of mountains still in motion. Nowhere is this more evident than in the slow convergence of the Indian plate with the Eurasian plate, a journey that began tens of millions of years ago and continues today. The result is the Himalayas, the highest mountains on Earth, born from a collision that has not yet ended. India, once part of Gondwana, broke away from Antarctica and Australia, and drifted northward with surprising speed, covering more than 6,000 kilometres in less than 100 million years. This rapid movement by tectonic standards brought the subcontinent crashing into the southern margin of Eurasia. The ocean between them, the Tethys, was closed in the process. Its seafloor subducted, its sediments scraped onto the continental margin, folded into the high peaks we see now. A poetic detail: the fossils of marine creatures still lie embedded in the limestone of Everest remnants of a sea, now miles above its former level. When India met Asia, the collision did not stop the plate. It only changed the nature of the motion. Because both plates are continental and relatively buoyant, neither could easily sink. Instead, the crust thickened, crumpled, and began to rise. Layers of rock, once horizontal, were compressed and uplifted. Faults developed, thrusting slices of Earth's crust over one another like pages in a book pushed from the sides. The Himalayas rose in this way, slowly, steadily, and still rising. Today the range grows by about a few millimetres each year, even as erosion works to carry it away grain by grain. Another irony: the tallest mountains on Earth are temporary structures growing and eroding simultaneously, caught in a perpetual contest between uplift and loss. The collision affects more than the peaks. To the north, the Tibetan Plateau, often called the roof of the world, has been uplifted as well, forming the largest and highest elevated region on the planet. Its interior is vast, dry and cold, shaped by the combination of tectonic uplift and the rain shadow cast by the towering Himalayas. The plateau continues to deform under the pressure of India's advance, resulting in strike-slip faults, extensional zones and crustal thickening that reshapes the interior in ways still being mapped. This is not a single collision, but an ongoing compression, a region under stress, continuously evolving. GPS measurements confirm that India continues to press northward into Asia. The convergence rate varies from region to region, but averages around 5 centimetres per year. Earthquakes are frequent and powerful. The faults along the Himalayan front, including the main central thrust and the main frontal thrust, remain active, storing strain that periodically releases in seismic events. Some of the world's deadliest earthquakes have occurred here, silent build-up released in moments of violent rupture. Yet even these events do not interrupt the broader motion. The plates continue regardless. Only took 50 million years to build the Himalayas. They are not finished. Other regions bear witness to similar continental collisions. The Alps rose when the African plate drifted northward and collided with Eurasia. The Zagros Mountains in Iran formed from the convergence of the Arabian and Eurasian plates. These ranges too are products of crustal shortening and thickening built not from dramatic episodes but from continuous pressure. The story is always the same: land meets land and neither yields. Instead, the crust folds upward. What differs is the pace, the angle, the layering of history beneath. A quiet irony, the landforms we see today are often the latest expressions of collisions that began long before mammals walked the earth. And yet the effects of these collisions are not limited to topography. They alter climate by elevating mountain ranges that influence atmospheric circulation. The rise of the Himalayas and the Tibetan Plateau helped intensify the Asian monsoon, shaping rainfall patterns for millions of years. They also expose rock to weathering, which draws carbon dioxide from the atmosphere and may contribute to long-term climate cooling. Tectonics once again shapes not just the land but the air and the sea. The collision zones also serve as archives. Within the thrust sheets and metamorphic cores, geologists find rocks that have been buried, heated, and brought back to the surface. High-pressure metamorphic rocks such as eclogites and blue schists record the subduction of crust during the early stages of collision. Their minerals tell of pressures and temperatures found tens of kilometers below the surface. When these rocks return to the light, they bring with them stories of depth and transformation. Another poetic detail: the oldest parts of mountains may be the ones least visible, buried not in earth but in process. And still the Himalayas rise, not evenly, not smoothly, but with the irregularity of real motion. Some segments move faster than others. Faults accommodate different types of strain. Uplift and erosion play out unevenly across the range. The system is dynamic, not static, alive with slow shifts that only make sense over centuries. One cannot watch the Himalayas grow. One can only measure that they are taller now than they were and less than they will be. Even in the depths of the earth, this collision leaves a mark. Seismic studies reveal a thickened crust beneath the Tibetan Plateau, reaching depths of over 70 kilometers. The Indian plate appears to underthrust much of the region, diving shallowly beneath the Eurasian plate. The interface between them is complex, marked by zones of high pressure, partial melting and irregular motion. This is not a clean subduction, but a continental crush, a zone where the lithosphere warps under its own weight. A final irony: two plates too light to sink still manage to reshape half a continent. And they do so quietly, persistently, grain by grain, quake by quake, year by year. The Earth's surface, despite all its movement, remains a puzzle with pieces that do not always fit. For all the clarity of spreading ridges, subduction zones, and collision fronts, much of the lithosphere still resists easy understanding. Its fractures are not clean. Its boundaries are not fixed. Across continents and oceans alike, the crust carries scars of earlier tectonic episodes. Cryptic sutures, reactivated faults, ancient rift zones long buried beneath sediment. These fragments, terrains, microplates, slivers of vanished oceans drift, collide and attach themselves like drifting pages binding into new volumes. Together they form a mosaic more complex than any single model can contain. Even the modern continents, so familiar in outline, are composed of pieces borrowed from others. Western North America, for instance, is a collage of ancient island arcs, seamounts and crustal blocks, the remains of long-gone plates sutured onto the edge of a larger craton. These accreted terrains came from all directions, delivered by subduction zones that vanished long ago. Their rocks tell of tropical reefs, volcanic arcs, and oceanic basins that now sit among mountains and forest far inland. Only took 100 million years to turn ocean into forest. A quiet irony: some parts of a continent were never meant to be land. Even within the interior of plates, structures remain active or reawakened under new stress regimes. Ancient faults once dormant can slip again when distant plates apply renewed pressure. The New Madrid seismic zone in the central United States, far from any plate boundary, still generates earthquakes, reminders of a rift that nearly split North America apart in the late Precambrian. The failed rift remains as a weakness, its ancient wound reactivated under stress transmitted from far beyond. The lithosphere forgets slowly. It keeps its memories in fractures. Transform zones also leave enduring marks. Along the Dead Sea, Transform and the North Anatolian Fault. The Earth's surface is sheared over time, cutting valleys, displacing rivers and altering landscapes. These regions may not see dramatic elevation gain like a mountain range, but they still speak in motion sideways instead of upward. A poetic detail, a stream diverted by a fault may travel kilometers over millennia, recording the drift of Earth in every gentle meander. Then there are the places where the lithosphere thins. Rifts such as the East African Rift mark the beginning of potential new plate boundaries. There the continental crust stretches and fractures, forming a complex zone of volcanoes, lakes and valleys. Magma rises, thinning the lithosphere further. The process may continue for tens of millions of years before a full ocean basin forms, or it may halt a failed rift abandoned like a sentence never finished. The crust is filled with such interruptions. Not every fracture becomes a fault. Not every rift becomes a sea. Many of these complexities arise because the Earth's outer shell is not made of perfect plates. It is riddled with transitions, gradations, and inherited structures. The boundaries between lithosphere and asthenosphere are not sharp. The crust varies in thickness and composition. Heat flow changes with depth and location. Water content alters the strength of rock. The system is layered and fluid, composed not of discrete parts, but of continuous overlapping processes. Another irony, the deeper the science, the less tidy the map. Microplates and diffuse boundaries challenge the simplicity of early plate tectonic models. In regions like the Western Pacific or the Indian Ocean, small plates jostle among larger ones, moving in directions that shift over time. Some microplates emerge as remnants of broken larger plates. Others are caught between converging giants, squeezed, rotated, and eventually destroyed. Their lifespans vary. Some persist for hundreds of millions of years. Others vanish within a few tectonic cycles. Their histories are brief, but their influence is real. They alter stress fields, affect subduction zones, and carry volcanic arcs to new locations. Plate boundaries themselves are not fixed. They migrate, lengthen, or die. Spreading centers can shift, as happened in the South Atlantic. Subduction zones can jump locations, as evidenced by the arc migration in Central America. When the direction of plate motion changes, the boundary adapts. New faults develop. Old ones become inactive. The system is elastic, reshaping itself in response to forces that emerge from within, and even the forces themselves are layered. Slab pull, ridge push, basal drag. These terms describe components of a deeper system where the flow of the mantle interacts with the rigid crust above. But mantle flow is complex. It is affected by deep heterogeneities, mineral phase changes, and the buoyancy of sinking slabs. No single driver explains everything. The Earth moves because it must, because heat needs to escape, and the crust is not uniform and the mantle stirs with inherited motion. In some regions, parts of slabs appear to tear. Seismic imaging suggests gap slab windows where subducted lithosphere no longer forms a continuous sheet. These windows allow hot asthenosphere to rise, generating unexpected volcanism inland of traditional arcs. Patagonia and western North America both show evidence of such features. They remind us that plates are not perfect rafts. They buckle, split, and deform even as they descend. A final irony, the pieces that seem most solid are the ones most prone to rupture. In all of this complexity, the guiding principles of plate tectonics remain sound. The lithosphere moves, the mantle flows, Crust is created and destroyed, yet the variations and exceptions matter. They tell of a planet not governed by rigid rules but by evolving conditions. The crust is not a passive shell, but a surface alive with inherited structure responding to forces both local and global. It is a dynamic interface where water, atmosphere, life and stone interact. And while we speak of plates, the reality is more textured, a patchwork of fragments drifting together and apart, never fully stable, never truly at rest. The continents continue to drift slowly and without purpose, carried by the invisible churn of the mantle below. They do not follow a destination nor return to a fixed point, but trace a path shaped only by balance between heat and pressure, buoyancy and density, resistance and release. Africa edges northward, inching closer to Europe each year. The Mediterranean, once a deep remnant of the Tethys Ocean, narrows. One day, not soon but surely, it will vanish, closed by the same slow motion that once opened it. The collision will raise new mountains, a sea will become land. This is how the world remakes itself, not in sudden events, but in drawn-out convergences spanning tens of millions of years. North and South America shift westward, driven from the mid-Atlantic ridge by the steady addition of new seafloor. The Pacific Ocean, ringed by subduction zones, shrinks around them. Its once vast basin narrows imperceptibly as its floor sinks beneath surrounding continents. Only took 180 million years to widen the Atlantic. It will take just as long to erase the Pacific. Australia drifts north, a lone raft moving toward the tropics, colliding slowly with the island arcs of Southeast Asia. Antarctica, surrounded by a circumpolar current that isolates it from global warmth, remains largely motionless, not from inertia, but from position. Yet even it drifts, turning slowly, its icy silence resting atop a continent of rifts and fault lines. These movements are tracked with astonishing precision. Satellites anchored to the stars above measure continental positions to the millimeter. We can say without irony how far Europe is from North America today, and how much closer it was yesterday. But this precision does not change the pace. The plates move slowly, far too slowly for any creature to witness with the naked eye. A poetic detail, a human lifetime might witness a plate move no farther than the length of a hand, and yet the accumulations are immense. A few centimeters each year adds up to thousands of kilometers across geologic time. In that time, continents rotate, ocean basins open and close, climates shift, ecosystems transform. Forests become deserts. Coral reefs rise and fall. Ice sheets advance, retreat and return again. The crust drifts, and with it everything anchored to it. The future is shaped by the continuation of these motions. Though we cannot predict every outcome, the broad outlines are knowable. Given enough time, Africa may weld itself to Europe, closing the Mediterranean and raising new mountains across southern Europe. The Americas may collide with Eastern Asia, reversing their current paths. A new supercontinent, Pangaea, Proxima Nova Pangaea, or Amasia, depending on the model, will emerge. Its formation may take 200 to 300 million years. Its shape will not mirror the past, yet it will follow the same logic: closure of oceans, collision of continents, compression of crust. Another irony: the paths of continents are never the same, but their patterns always return. The Atlantic, now growing, may someday begin to shrink. Subduction zones might initiate along its passive margins, reversing its expansion. Where today we find stable coastlines, future trenches may form, and with them arcs of volcanism, uplift and seismicity. The old becomes new again. The quiet breath of tectonics is one of recurrence, not repetition, and beneath it all the engine continues. The mantle flows, transporting heat outward. Slabs sink, dragging surface with them. Plumes rise, weakening crust and feeding volcanism. The cycle of crustal renewal of spreading subduction and uplift depends entirely on this motion. Without it, the crust would stagnate. Erosion would wear mountains to flatness. The oceans would grow wide and deep. The Earth would become quiet like Mars, like the Moon. But Earth is not quiet. It shifts not dramatically but continuously. The continents we know are transitional. Their arrangements are temporary. Even the names we give them, Asia, Africa, America, apply only to the present configuration. Their foundations extend far deeper and longer. Cratons that formed 3 billion years ago still underlie modern land masses, their deep roots surviving countless collisions and rifts. These ancient cores have drifted across the globe many times. Some once belonged to different supercontinents. Others were joined, then severed, then rejoined. The Earth remembers its shapes in fragments, not wholes. Another poetic irony: the most permanent part of a continent may be the one most hidden from view. These long-lived cratons serve as keystones around which new crust accumulates. They preserve records of Earth's early history rocks that formed when the planet was young, when oxygen was scarce, when life was microbial and oceans boiled. These regions, stable and thick, resist subduction. They drift through time as survivors anchored in slow motion. And still they move. Nothing is fixed. The future will inherit a world whose surface looks nothing like today's. What is now ocean may become mountain. What is now desert may lie beneath the sea. Cities built on stable ground may one day rest near the edge of a growing rift or a future collision zone. The motions are too slow to change daily life, but too vast to ignore across epochs. Humanity exists in a narrow window, a sliver of time in which the continents are arranged as they are. We build maps, draw borders, chart coastlines. But the Earth is indifferent to these. It continues its motion, reshaping itself beneath our feet, and one day, far beyond our memory, the maps will be rewritten. Only took a few 100 million years to build the world we know. It will take just as long to lose it. Yet in this impermanence lies something quiet and grounding. The tectonic dance is not chaos. It is continuity. A slow rearrangement of parts governed by the steady flow of heat, the balance of density, the inevitability of motion. The continents drift not toward an ending, but through an endless unfolding. And now the motion slows. The restless continents, though still adrift, begin to fade from focus. The invisible churn of the mantle continues beneath a crust that holds oceans, forests, ice and flame, but we step gently away from that great machinery. Let it turn without our watching. Let the plates slide and fold in their own time. The mountains still rise, the seafloor still spreads, the trenches still deepen. But here at the edge of this long drift through geologic time we pause. The details blur into texture, the processes into rhythm. The Earth has never stopped moving, not since it first cooled into layers, not since its surface fractured into rafts of crust floating on a sea of stone. But that motion measured in millimeters per year, in eons per rotation, does not rush. It waits. It carries everything without hurry, the continents that cross hemispheres, the ocean basins that open and close the scars of ancient collisions pressed into bedrock. Nothing is finished. Everything is always beginning again. Beneath cities and deserts, jungles and glaciers, the slow exhale continues. Beneath the silence of night, the plates drift still. The planet does not rest, but we can.